Okay, great. Welcome back for the last talk of this first day of the conference. And so we have Andrea telling us that black holes are really just strings, I think.
That's right. Once the okay. So thanks a lot. Thanks a lot to Joseph and Nick for organizing this conference and for inviting me to speak. Nick originally requested me to speak about something completely different, but I refused. So thanks nevertheless for letting me talk. So I thought this would be more fitting for this conference, and it is indeed the proposal for how black holes that are rotating can be interpreted as strings. And so this has been a very fun project that we are in the process of finishing. And who's we? So this includes two fantastic postdocs who are in the audience. So there's Nate Chaplak, where are you? Over there. And Maria Tomasevic over here. And Roberto Emperan, who most of you probably know is one of the foremost experts in the world about rotating black holes in general dimensions. And I should maybe pause here for a moment to give an apology to some and a disclaimer to others. So when I was looking for the name tag outside when I arrived this morning, I didn't find mine. So I saw Roberto's, who is not here, so I claimed that. So apology to Roberto, who is maybe watching over Zoom. I couldn't resist the temptation to pretend being you for a day. So that was the apology. And the disclaimer is that although I've put on the Roberto patch, that does not mean that I will be able to answer any questions that he will be able to answer. So sorry for that. Okay. So I want to talk about the correspondence between rotating black holes and fundamental strings. Or not. Okay. So this just worked 5 seconds ago, and now it doesn't. Okay, let's do that instead. Okay, so black holes exist. At least that's what we believe, and that's why we're here. And we have these marvelous experiments that give us strong evidence that this is indeed the case. But like many of you here, the question that I'm interested in is, what are black holes actually made of? So while this is foremost the phenomenology day today, I will end by discussing something very abstract, which will be very hard to measure in the foreseeable future, but nevertheless are things that we have to understand if we want to say anything about the microscopic structure and ingredients of black holes. So we're interested in the question, what does the entropy of a black hole, which is given by the area over 4G Newton, what does it count, what does it mean? And there are some proposals. I don't have to tell this audience that most of our key insights about this question come from string theory, where we have a statistical explanation of the entropy. And I put an asterisk here because there's also been recent beautiful results using holography and the Euclidean path integral, which I think we'll hear also more about in the course of this week. But one thing about this window into black hole entropy from string theory heavily relies on certain symmetries, in particular supersymmetry allows us for an exact accounting for the entropy. And I put another asterisk here because we also have results for near supersymmetric and non-supersymmetric extremal black holes. But most of our understanding comes really when we have supersymmetry. And obviously, the Schwarzschild black hole or generic Kerr black hole does not fall into that category. And so the question is, what do we do about that? So can we go beyond this supersymmetry regime for an accounting of the entropy? And the answer is in some sense yes, but it will not be an exact matching. But that comes as no surprise to anyone. So in the course of this talk, we'll be thinking about the proposal that black holes can actually be viewed as strings. And so now let's start gathering some evidence. So black holes are massive, large, highly degenerate objects. Strings have massive, large, highly degenerate states. Check. But we can do a bit better. So stationary black holes have to obey the Kerr bound, which says that the angular momentum is bounded by the mass squared. Now, strings also satisfy some bound on the angular momentum called the Regge bound. Check. What about the entropy? So that's the thing that we want to match and understand. So the black hole entropy scales with the mass squared. On the other hand, the degeneracy of string states just scales with m. That's too bad. And if this was it, then my talk would be over, which obviously is not the case. And what we have to do here, we have to take into account that actually we have units. So the entropy is a dimensionless number, and I've written down something dimension full. So we have to describe this in some units, and we better use the same units to match two things that are supposedly equal. The upside is that this last point that didn't check out will actually check out in some form. The downside is that what we thought checks out actually doesn't, and there's some very interesting physics going on there. Okay, so before talking about rotation, let me state what the correspondence is for static black holes. And this goes back to the 90s, to the work of Susskind, Orad Sporczynski, De Moor, Veneziano, and others. And the statement is the following, that if we start with a black hole and we change the string coupling, we can go from the black hole to the string and back. And in the middle, there's a region where the black hole should transition into a string, or conversely, where the string should transition into a black hole. And we would like to understand this correspondence in a more precise way. So let me talk again about black hole entropy, but now put units. So this is scales mass squared, but in Planck units. On the other hand, the degeneracy of strings scales with the mass, but now in string units. Now the Planck and the string units are related to each other by a factor of string coupling. And so if we express the black hole entropy in terms of string units, then we see that for a certain value of the string coupling, these two entropies at the same masses can actually agree. Now, I said we changed the coupling in order to go from the black hole to the string and back, but what's actually a physical process for changing this coupling? Furthermore, this process should be adiabatic if we go from a black hole to string and back. What is the curvature of the geometry as we change the coupling? Then the objects here, they evolve and they may radiate. So what happens when we take that into account? And then finally, what happens when we add rotation? Yes? Where's the cube?
So I guess in all these literature, this word adiabatic is used quite a bit. Like, what do we precisely mean?
I will talk about that.
Okay.
Yeah. So this will be part of the first part of the talk, which is reviewing the statement of the correspondence between static black holes and strings. I will flesh out some details, including what we mean by adiabaticity and some others, which will be particularly crucial for talking about rotation. And then in the second part of the talk, I will discuss this sort of new proposal for how rotating black holes can be identified with strings. And there will be some puzzles, like the one that I hinted to, and we will resolve them. OK, so let's start with static black holes and fundamental strings. So let me review some features about those two objects. And let me first remind ourselves about the different scales involved here. So we have the string tension, 1/2 pi alpha prime, which is related to the string mass and the string length in this way. The strength of interaction given by Newton's constant can be expressed in Planck units with this power that depends on the space-time dimension d, or in string units where we pick up this extra factor of the string coupling g to the power 2. Now, the string coupling can vary in space and time, and we express this by the change of this scalar field, the dilaton, phi. And our physical process for varying the coupling and achieving this correspondence from black holes to strings and back is by letting a dilaton wave pass with a very low wavelength. And let me mention here that unlike in some other talks, I'm setting h bar to 1, c to 1, and I drop all numerical factors because they will not be important. As I said in the beginning, this will not be an exact accounting of the entropy, so we'll forget about all those sort of irrelevant to first approximation factors. Okay, now black holes. So static, neutral black holes in d dimensions with mass m have a horizon given by the Schwarzschild radius, so g times m to some power in the space-time dimension. Expressed in Planck unit, this looks as written here, but we can also write this in terms of string units, and then we pick up this extra factor of the string coupling squared. Now we can talk about the curvature. So the Kretschmann scalar is proportional to 1 over the area of the black hole, so the horizon radius squared, which is given by this expression, where we see that the string coupling appears in the denominator. And so what this means is that as we reduce G, the curvature increases. And so at that point, once the curvature gets very large, we do not trust the black hole geometry, the black hole metric anymore, and something else has to take over. When G squared reaches the inverse mass in string units, then the horizon becomes of string size. So this is the place where we expect the transition from a black hole to a string to happen. And similarly, if we start from a string, it's at that, and we increase the coupling, it's at that value where we expect the transition into a black hole. Now, once again, the comparison of the black hole entropy and the string entropy, but now in general dimensions. So the Bekenstein-Hawking entropy is given by this expression now, which depends on D, while the string entropy is still given by the same expression. And we now see that if we tune G squared to take this value above, so the inverse mass in string units, then for the same mass, these entropies agree. And we can succinctly write this as the string coupling squared being given by 1 over the entropy. And so this marks the correspondence point between a black hole and a string.
Sorry, I have one more question. Why should this matching happen at L string? Because the size of a string gets bigger because of the random walk nature, right? So
yes. So I'll get to that. If you allow me, I'll go in order, and then I'll address both your questions. Yes.
Here. So you impose that matching G squared equal 1 over S. So different black holes will have different entropies. So you're requiring that for each black hole, the value of G has to be that. So it's like a selection rule in some. I don't know. It's does it arise from the formalism, or is something you're imposing for all the different black holes?
For every black hole, if you write down the entropy, the transition between the black hole and the string will be given by this 1 over S, whatever S is.
Okay. So it's not imposing.
The point is we have a string configuration and a black hole configuration. And what we will want to do is we want to fix the entropy. So we want both systems to have the same entropy. And then we want to change the coupling. And then we want to see if one can go into the other. And when we fix the entropy and we change the coupling, as you see from these expressions here, the mass has to change. So both the mass of the string and the mass of the black hole will get renormalized as we vary the coupling. There's another question.
So I'd like to make 2 comments. So first of all, the scaling of the entropy, the agreement between the string and the black hole, was pointed out already in 1993.
Okay.
And one other point is that a physical mechanism for achieving the transition is the conventional Hawking radiation. So this was suggested in the paper in 86. You mentioned this Dalton wave.
I'll have that in a second. So if you let me continue or not.
Why? So this is the transition in the microcanonical ensemble, right? So why is it clear this is where I should look for it versus the canonical ensemble of my system?
Okay, so we'll start somewhere, and I'm giving you evidence as we go along. So if I get to go along, then I will give you more evidence for this transition.
I was just asking whether there's a picture in the. I mean, this is related to the adiabatic question that was asked earlier. Why microcanonical versus canonical ensemble in this story here? Say that again.
It's harder. Watch out.
It's harder to discuss in the canonical ensemble simply because there's a limiting temperature on the string side. So it's easier to discuss in microcanonical ensemble because you're just talking about the density of states as a function of energy. And then there's some transition energy where you go between black holes above that energy and strings below that energy. And the problem is that if you try to do that microcanonically, there is no unique association of a string mass because of the temperature is always the same in the Hagedorn phase.
Okay, so once we fix then the entropy and we vary G, the mass is to change. So the mass of the black hole and the string gets renormalized. So for the string, we expect the change in mass to be small, to scale with G squared for small g. And then for the black hole, if you turn around the equation that I've written in the previous slide, the mass changes with G according to this expression. But at the correspondence point, where G string is 1 over the entropy, these two match. And so if we draw these adiabats, so the curves along which the entropy is constant, both in the string regime and in the black hole regime, at the place where G string is 1 over S, these two adiabats meet. Okay, so that's the first check. So this suggests a picture where we can go from a black hole to the string and back. And we can follow this evolution adiabatical, and I'll get to the point of the adiabats in a moment. And so this picture works well when we have a large degeneracy of states, and we can go between a black hole with a large entropy to a string with a large degeneracy of states and back. And so this picture suggests that there is a microscopic understanding in terms of the black hole entropy at the correspondence point in terms of strings. Now, a few important details. Okay, so first of all, this was Raghu's first question about the size. So actually, there's a discrepancy between the string size and the black hole size. So I said that the black hole goes into a string once the black hole reaches string size. But the string at that point, because it can be well modeled by a random walk, will be much bigger. So in a random walk model, the size of the string, which is given by the square root times the length times the string length, which is given by the square root of the entropy times the string length, is much bigger than the string length, whereas the black hole has string length size. But what we have done here is we have neglected the effect of self-gravitation in the string. And once we do that, the string will actually shrink. And this is the famous work of Horowitz and Wojcinski, which have had several follow-ups in the recent years. Okay, so this is a way to actually make the sizes of the black hole and the string match. Next, we have to talk about dynamics, because once the string coupling is any finite number between 0 and infinity, neither strings nor black holes will be stationary anymore. So the self-interaction of massive strings means that they will decay, so they can either fragment or they can emit light strings. On the other hand, there are quantum effects in black holes, and so they're also not stable. They can decay via the emission of Hawking radiation. So in particular, if we look at the decay rates of both the string and the black hole, which are given by this expression here, we see two things. So when G is 0 or infinity, then we have stationary solution, but anything in between decays. And there's a maximum of these decay rates that is reached at the correspondence point. So G string squared is 1 over S. Now about adiabaticity. So we're interested in the rate of change of the system, this expression. So the change of the coupling over the coupling, which is the change of the dilaton. And we want this to be slow enough so that we don't excite the state. I already mentioned before that we can achieve this varying of the string coupling by a dilaton wave, and we give it a long wavelength so that it doesn't excite the state. On the other hand, we want this to be fast enough so that the entropy doesn't change. And the problem here is that at any finite coupling, as I just said, we have radiation or some form of decay. Now, it turns out that there is actually a range of adiabaticity, so that this process is not too slow and not too fast. It's given by these boundaries here, expressed in the string length. Where does this come from? So at the correspondence point, the size of the black hole is of the order the string length. We want a wavelength that is long enough not to excite it. So this means that this parameter is smaller than 1 over the string length. At a temperature T, a quantum is emitted every thermal time 1 over T. And so the loss of entropy in the time interval delta T gives an entropy change that's proportional to delta T times the temperature, and that we want to keep small. At the correspondence point, the temperature scales with one of the size. And so that means that what we want here, so we don't want the change in entropy to be large, we want to keep it small. So that means that delta T inverse has to be bigger than the temperature over the entropy, which is at the correspondence point, 1 over the entropy times the string length. And so this gives these two boundaries here. And for large enough entropy, it means that there's ample room to satisfy this adiabaticity criterion. But it should be noted that for any finite entropy, there will never be an exactly adiabatic process. I hope this answered your question. If not, you can follow up or we discuss afterwards. Okay. Okay. So now about this other point, if you don't like the dilaton wave, you can also let the black hole evaporate. Now the coupling stays fixed, but the mass decreases, and we can still keep the entropy fixed. And the process is now by emission of Hawking radiation. And the natural expectation here is that once the black hole becomes small by emitting mass through the Hawking process, that it turns into a string. But unlike the dilaton wave, now we don't get to choose the transition rate. However, if the coupling is small enough, then the rate can be small enough, so the evolution can be slow. And since the string coupling is 1 over G string squared at the correspondence point, which is much larger than 1, and then the loss of the entropy through radiation is small if the transition happens during a few string units of time. And so in that scenario, the evolution from a black hole to a string can be slow enough so that it's almost adiabatic. So this is then another way of talking about the transition between black holes and strings. Okay, so let me summarize the correspondence for static strings and static black holes. So it relates black holes to weakly coupled strings and gives a statistical interpretation of the black hole entropy. It can be realized by this passing of a dilaton wave or by evaporation. And it applies to generic black holes in general dimensions. Let me emphasize here again that this is not an exact accounting of the entropy. We can't get the numerical factor via this idea. And another comment, I'm saying here that generic black holes in general dimensions, but so far we have only discussed static black holes. And so rotating black holes are next, but first, Amy has a question.
Yeah, so it sounds like in the way you're describing things that you're imagining that this transition is like a crossover rather than a phase transition. What is the evidence for that? So
I've actually not discussed either or, because in order to actually treat the regime where the black hole turns into a string or the string turns into a black hole, you need to do better than the free string approximation. And so I cannot say from this picture which it is. And so when I talked about the size, it's the Horowitz-Polchinski self-gravitating string model that actually better describes the regime where by taking into account gravity in the string description. And so I haven't discussed that actually, but this is important in order to sort of get a more precise picture of the transition. Okay. So now let's turn on rotation. So actually and now by the power bestowed upon me by wearing the Roberto badge, I can now tell you something about the rotating objects. So first, let me start with the point that in general dimensions, there's actually a zoo of black hole solution and a zoo of strings, which is not there in 4 dimensions. And it will be very convenient to introduce 2 scales that allow us to characterize this zoo. And those are what we might call the mass length and the spin length. So the mass length in 4 dimensions would just be the Schwarzschild radius, but in high dimensions it isn't. But nevertheless, G Newton times the mass to some power in the space-time dimension is a useful length scale. And the other one is given by the angular momentum divided by the mass. Okay, so Now there are two regimes, one where the spin length is smaller than the mass length and the other way around. So when the spin length is smaller than the mass length, we are in what we call the Kerr regime. So there we have black holes that are sort of roundish. They're unique, and they are dynamically stable. And then in the other regime, which we call the ultra-spinning regime, we have more to play with. So we have more pancake black holes. They have different shapes. There's also different topologies. So we have black rings. And these are in general dynamically unstable. Now, there are also string configurations that are more roundish and string configurations with different kinds of shapes. And there's also configurations more recently discussed where you have sort of hybrid, where you have a black hole that has a string sticking out. OK, so lots of different objects in high dimensions. And what we will focus on is we look at objects that rotate in a single plane. So this is a convenient simplification, but it also captures the most extreme features that rotation adds to the game. And we will discuss the adiabatic invariance, so the entropy and the rotation in terms of this single rotation plane scenario. OK, so I've said we want to keep the entropy fixed in order to match the black hole and the string system. And let's start with 4 dimensions. So in 4 dimensions, we have the Kerr bound. So this can both be expressed in terms of this mass and spin length, or in terms of the angular momentum and the spin. And here, this is an existence bound. Beyond this bound, no stationary black hole solutions exist. And we can, again, draw the mass in Planck units squared for fixed entropy. And we see that black holes exist for all values of the angular momentum up to the Kerr bound, where, as I told you, I'm always dropping numerical factors. But here in this picture, I've reinstated them, all the 2's and pi's. And we also have the extremal limit in 4 dimensions. Now, there's a bound that I talked about that exists also for strings, the Reggie bound. So we have the Kerr bound on one side for the black holes, and we have the Reggie bound on the other side for strings. And naively, I told in the beginning, naively, those bounds look as if they match. But then if you take into account units, they actually don't. So what's going on here? What's the relation between these 2 bounds? OK, so the Kerr bound is given by the mass squared in Planck units. When we express the Planck mass in terms of string mass, then we pick up a factor of the string coupling. And for small enough coupling, this is much smaller than the mass squared in string units, which is the Reggie bound. So we have that the Kerr bound is much smaller than the Reggie bound. So let's look at what are all the objects that we have and where do they lie in this on this J line. So we have strings up until the Reggie bound, and we have black holes up to the Kerr bound. And then so naively, from this consideration, it looks like there are no black hole counterparts to highly spinning strings. So that's the first puzzle that we encounter when we add rotation. OK, next, let's go to high dimensions. Let's see what happens there. Again, we're looking at fixed entropy diagrams. And we are comparing, we're looking at what happens to objects below and above this bound. We will still call it Kerr bound in high dimensions. But here, it's no longer an existence bound. It's a stability bound. There are still stationary black holes that can exist, but they will be unstable. So the diagram here looks like this. For small angular momentum, we have the Kerr regime. Then as we cross the Kerr bound, we go into this ultra-spinning regime. And we have these high-dimensional Myers-Perry black holes whose mass in Planck units to the dimension -2 scales with the square of the angular momentum. And then we also have other kinds of shapes for the black holes, such as black rings with different horizon topologies. And they in particular scale almost linearly in J. So there are different objects in high dimensions, which we all have to take into account in order to make sort of a proposal for a correspondence between black objects and strings. So let me make a comment here. There exist also extremal solutions in 5 dimensions, but the entropy is 0. And so if we keep the entropy fixed, we will never reach it. It can only be reached once you set the mass and the angular momentum to very large values. And then in higher dimensions, there exist no extremal solutions. And the other point is there's actually two branches of black rings. There are fat black rings and thin black rings. And the first behave more like Myers-Perry black holes. And the latter, they're more highly spinning objects. Okay. So now let's talk about this rotation bound that I mentioned, but now in higher dimensions. So on the black hole side, we have black holes in the Kerr regime, which are almost round, while in the ultra spinning regime, we have all these different objects. On the other hand, in the string regime, we have the roundish string balls, and then more highly spinning strings, but only up to the Reggie bound. So the second puzzle is that there seem to be ultra spinning black holes that have no stringy counterpart. Now, wait a second. So actually, what happens if we look at fixed entropy diagrams is that the Reggie bound goes to infinity. So this here goes to infinity. And so then naively, this puzzle is actually a non-puzzle. But it turns out that there still exists a mismatch between the kinds of strings and their shapes that should go over into black hole solutions. So there exists still a mismatch between black holes in the regime between the Kerr and the Reggie bound, which goes to infinity in fixed entropy diagrams. Okay, so we have these two puzzles. There seem to be no string or black hole counterparts in certain regimes. And the question is, how do we resolve this puzzle? It turns out that both puzzles hide an assumption. And the assumption is that we are trying to match stationary solutions. But we have already discussed that ultra-spinning objects are dynamically unstable. Highly spinning strings, they are not stable either. So we shouldn't be forcing ourselves to match our stationary solutions. And actually, we should take into account dynamics. And that will resolve our problems. OK, so let's resolve those problems. OK, so let me start by discussing some features of rotating black holes that will help us understand how these issues can be remedied. OK, let's talk about horizon shapes and curvatures. So I talked about the Kerr regime and the ultra-spinning regime. And different physics is going on in these two regimes. So in one regime, we have black holes, which in general number of dimensions are nice roundish objects. Their curvature, so the Kretschmann scalar in particular, is almost approximated by the static value. And yeah, almost approximated by the static value. And then in the ultra-spinning regime, we have to discuss black holes and black rings. So in 5 dimensions, black holes have curvatures which along the rotation axis and in the equatorial plane are given by these two expressions, where we see that it's small for large angular momentum. This is small around the rotation axis. But in the equatorial plane, this becomes large. And it becomes large both for taking the angular momentum large, but keeping the entropy fixed, or by making the entropy small and keeping the angular momentum fixed. OK? And these objects are highly distorted in the equatorial plane, where the curvature really becomes large, as you can see from here. And thinking about what happens to the curvature is important to understanding when and where the transition from a black hole to a string appears. Because when the curvature goes large, the geometry is no longer a good description. Then in 6 dimensions and higher, it looks a little different. The black holes now get pancaked and have large curvatures near the equator, as well as along the polar direction, the rotation axis. But unlike in 5 dimensions, they never develop naked singularities. So 5-dimensional black holes and 6 or higher are somewhat different in many respects. Then we have black rings in 5 dimensions or higher. And they have lower curvature than these rotating black holes, so the Myers-Perry black holes with the same entropy and spin. But it's still large as J goes larger. OK, so we have discussed a bit the curvature and seen that black objects in 4 and 5 and 6 and high dimensions, they're slightly different depending on where the curvature grows large as the angular momentum is increased. Now, what about stability? So I said we have to be careful about taking dynamics into account. So what happens to black holes under evolution is important. So in the Kerr regime, where black holes are roundish, they're classically stable. On the other hand, in this ultra-spinning regime, they're unstable. And so this applies for black holes in 6 and higher dimensions, and also for black rings in any dimensions larger than 5, larger or equal than 5. So we have two kinds of instabilities mainly here. One is so-called bar instabilities, where these black holes, they're bar-shaped, and they rotate very fast. And as they rotate very fast, they emit excess spin through radiation. And then these bar-shaped black holes, they become more roundish, so they go back into the Kerr regime. So that happens in this instability. There's another instability, the granular flum instability, which has the effect that black holes that have the extent, which is in one direction, when you perturb it, creates sort of ripples, and then makes the black object fragment. So I've drawn here the cylinder. If you put some perturbation along the cylinder, it will fragment into black holes. And so we can have black objects that fragment into other kinds of black objects. So there's two instabilities via radiation and via fragmentation, which will determine the dynamics of black objects in the ultra-spinning regime. And this we have to take into account when we try to transition from these black objects into strings. Okay? So now let me discuss some features of rotating strings. Maybe let me ask, is there any question about the rotating black hole properties before going on?
Which of the two instabilities that you talked about has a higher probability?
So the bar instabilities here, they happen predominantly in sort of a middle range of ultra spins, while the fragmentation happens at higher angular momentum. So if you have objects that are highly spinning, they will decay via the granular flum instability. And if you have objects that are moderately highly spinning, still above the Kerr bound, and if they are bar-shaped, then they will decay via radiation. But I should say that the decay rates, so this has not been completely, so there hasn't been a complete scan of all the black holes or black objects that we know and how fast they decay. So here I'm focusing in particular on black objects with simply connected horizons. So I'm discussing black Saturns, which could also be added to the picture. So there are many, there's a whole zoo that I'm even not discussing here, and many solutions are not even known analytically. So for the bar instabilities, there are some results if you go to large dimensions, where I have some analytic sort of window into discussing them. But in general, you would have to do a numerical analysis depending on how complicated your system is. Yeah. Emil, do you have a question?
Yeah, so in the fragmentation case, the system is still bound?
Yeah, okay, that depends. So it depends a bit on the spin of the system and what it decays to, but in principle, yes. So yeah, it depends on some of the details. No. But if we want to transition, the thing that transitions into, so it could either go into multiple black objects and then fall apart, and then you follow each black hole as you vary the coupling into a string regime, or it's still a bound state, and then you follow it, and then we will see what it can transition into. So this was the puzzle that, okay, there are some black configurations. Now it's even worse, because now we also have these fragmented objects, and what do they correspond to once you lower the coupling? Yeah. There are a lot of things when you add rotation and in high dimensions that haven't been fully explored. And one reason is that the analytic control is not always given. So. Okay, now let's go to strings. And in view of time, and since it's the last talk of the day, I will be rather brief here. So let me just discuss two features here, which is the density of highly excited string states and the size. And let me start with static strings. So we imagine we could start with a classical string and then quantize it. And once we've done that, we can write down a Hamiltonian, the Wojcik Hamiltonian, which is given by, in terms of oscillators. If we're in light congauge, we have D-2 transverse oscillators. So the Hamiltonian is given by D-2 of those. And we sum over the level n. And then we can compute the partition function, which has now D-2 of those factors from all these oscillators. and beta here denotes the inverse temperature. Now, in the thermodynamic limit, so high temperature or small beta, we can write down a very simple expression for the partition function. The leading term is given by this exponential here that goes like 1 over beta and comes with the d minus 2 oscillators. And then if we add also logarithmic correction, this will give us this additional polynomial in beta factor out front. Okay, so now we want to compute the density of states. So the partition function can be written as this infinite sum here, where this dn is the density of states that we want to extract. So we invert this expression, we integrate over beta. Turns out that the resulting integral can be solved by in a saddle point approximation. And the result that we get is the density of states that everybody here is familiar with, which goes like e to the square root of n times some factors. What about the size? So we can also compute the size of strings. So the size will be given essentially by the square of xi, where I can be any one of those directions from 1 to d minus 2. So we can just pick one of those because the size in every direction, since it's spherically symmetric, will be the same. So this is given by this expression in the oscillators. And when we invert this expression, we can again solve the resulting integral in a saddle point approximation, and we can write down what the size for an level n highly energetic string state looks like. And it scales with the density of states at level n multiplied by something square root in n. And we've heard already at some point today the term random walks. So this behavior of the size of strings is what we would expect from random walks. So the typical string size is now given by dividing this coefficient in this expansion by the density of states. And this is proportional to the square root of n. And that's what we would get from random walks. So remember, the square root of n is proportional to the mass, which is proportional to the string length. So that is what we expect. So that's great. And that has been done in the 80s. So now we want to go and generalize this to rotating strings. Okay, so how do we do this? So we can do this by adding a term in the Hamiltonian that comes with the angular momentum and some Lagrange multiplier, the angular velocity. And I said I will take angular momentum in just one plane. So let's take the 1, 2 plane as the rotation plane. Then the angular momentum can be expressed for the string in terms of the oscillators, so alpha 1 and alpha 2. And the partition function now, what happens is that because in the rotation plane, the oscillators 1 and 2 talk to the pieces in the angular momentum. So instead of having a d minus 2 over here, we have a d minus 4. And 2 of those factors, they talk to rotation. So this gives us these extra 2 factors, which have omega in the exponent. Now, again, we want to look at the high temperature regime, so the thermodynamic limit. And in that regime, we also get a very simple expression, which corrects the previous one just by this simple factor, omega divided by sinh pi omega. And now, this unfortunate extra factor complicates our life quite a bit. But nevertheless, we can make some headway in computing the density of states and the strings. We just have to work a little harder. So now the partition function also has an extra term e to the beta omega j in there. And we have to solve 2 integrals in order to extract the density of states. But this has been done, at least in some limit of large rotation by Russo and Susskind in the 90s. And this happens again, similarly as to the case for static strings via saddle point approximation. Now, what about the size of strings? So in the static case, this was a simple expression in terms of the oscillators, and you could pick any direction. But now, because the rotation is in a particular plane, so the 1, 2 plane, the result will be different depending on whether you choose I to be 1, 2 or any of the others. So we'll have some size in the rotation plane and some size perpendicular to it. And now the question that I want to ask before talking about the correspondence and concluding is making sure that the string that rotates is actually squeezed in the direction perpendicular to the rotation, so that it actually shrinks what we would expect. Yeah.
So in the previous slide, you had a formula for the size squared, and you are saying that it's proportional to the degeneracy. This formula of Rn squared. I believe you want to divide by the degeneracy.
Yeah, that's what I do here.
Oh, okay, fine. Now I understand.
So
okay, thanks.
this was just extracting the coefficient.
Yes,
the coefficient
yes,
scales with the density.
Okay.
The physical size is we have to divide by the density, and then we get the random walk result. And now when we go to rotation, what we have to do, we have to now again compute the density of states, but now including rotation, which is more complicated, and then extract this coefficient and then divide. Okay, so that's what I said here. That's what we have to do. And I will focus on the direction perpendicular to the rotation plane and try to see if the size actually shrinks as we crank up the rotation. And there's three regimes that are of interest. One is if we have slow rotation, the results that we expect is that the string is still kind of roundish. Then large rotation, which is what Russo and Susskind looked at for the density of states. So that means that J scales with N. And then the regime in between, which is more the typical regime, where we find most of the entropy of the string states to come from, which is when J scales with the square root of N. Okay, so for the density of states, what we find is the following. As we expect, for slow rotation, the leading contribution looks like that of a static string. And what's interesting is that in this ... the first correction comes from dependence in J that is quadratic. On the large angular momentum regime, Russo and Susskind found this expression for the density of states. So it gets modified from factors of square root n to factors of square root n minus j. And then for typical strings, there is more to be, it's a bit more subtle, and the expression looks more ugly, but you can find it. And actually, in all of this, I've been omitting talking about the logarithmic correction, which would give polynomial factors, which are also important to get right. Now, what about the size? So we have to compute this coefficient and then divide by the density of states. So it turns out that for rotating strings in the size perpendicular to the plane, you get square root n, which is the static result. And the first corrections, again, come with the square of the angular momentum. For typical, well, let me start here. For highly rotating strings, the size is now not square root n, but square root n minus j. So indeed, as you crank up j, the size shrinks in the rotation, in the perpendicular to the rotation plane. There's another question or comment?
When I tried to reproduce this calculation with at large j of order ON, I noted that the saddle point approximation breaks down when j is equal to n.
Yeah.
So you're assuming that j is parametrically larger than little n when you're saying this?
Yeah.
Okay.
Also, if when j is equal to n, okay, so then you would see, okay, this would go to 0. And you would also, so one thing that you have to do is normalize the density of states correctly, because you expect only to find one state at that value of j. Yeah. So we take it off the order n, but not exactly equal to n. And then for typical strings where j is of order the square root n, the expression becomes a bit more complicated. But it also shows that the size shrinks in the direction perpendicular to the rotation plane. So that's great. So that means that indeed the string gets squeezed in this perpendicular direction, which is what we expect. And sort of that is a justification for drawing all these pictures where the string, as you spin it up, gets actually squeezed and takes on different shapes. Okay, so now in the final few minutes that I have, let me now state, putting all of this together and state the correspondence for rotating black holes and strings. Okay, so let's start with strings and go to the black hole regime. So here we have these roundish strings in the Kerr regime, and we have highly rotating strings, which I denoted just by this simple, by this single string drawing. When we go to the black hole, the roundish string becomes a roundish black hole. That's what we expect. And now, as we crank up j, we have other objects to go into in the ultra spinning regime. So in higher dimensions, there was no puzzle. We had all these other objects available. But in 4 dimensions, I told you that there are no black hole counterparts to highly spinning strings. because we forgot that we could have stationary solution, but they could be, we couldn't have stationary solutions, but now we take into account that we have dynamics. And so strings can actually go into other kinds of objects. They're not stationary. And so the correspondence will go a little bit to the left here in this diagram, and you can lose angular momentum as the string radiates. Okay, so strings to black holes in all dimensions makes sense. So that solves puzzle 1. And now let's go from black holes to strings. Let's start with 4 dimensions. So in 4 dimensions, we're interested in the Kerr solution. So we have these roundish looking black holes up until the Kerr bound, and they go into roundish strings. There was no surprise there. But now in high dimension, what happens? So in 5 dimensions, we have these other objects beyond the Kerr bound. Again, the roundish ones go to roundish ones, no surprise there. But in the ultra spinning regime, we now can have the black holes that are highly pancaked and the black rings first decay into other objects, in particular into these hybrids, and also fragment into multi-black hole configurations. But now, before we had a puzzle that there was no highly spinning string analog, or no string analog that sort of matched in shape and form. But now we know that we actually should be looking at multi-string configurations that come from multi-black holes, and these sort of more hybrid-shaped objects can become highly distorted string configurations. So puzzle 2 is solved. There are ultra-spinning black holes with stringy counterparts.
Those are rods or they are these? They are particles from the thing
So which was here on the black hole side?
on the black hole side.
So here I've drawn hybrids, but you could also have rods. In high dimensions, you can have bars, which is what I want to draw next. So in the high dimensional, so 6 and higher, what happens is that you can also have these bar shaped solutions, which are stable enough so that they can stable long enough so that they can transition into something, and they will also go over into some highly spinning string configurations. So the important point here was to take into account that we should not just look at all the stationary black hole solutions, but we should take dynamics into account, and then these objects can decay into other objects, and they can then transition into strings. And this process, depending on the spin and depending on the time scales, can go over into string configurations adiabatically. Okay. So let me summarize this. So I've discussed a correspondence between rotating black objects in general dimensions and fundamental strings, which could give a statistical interpretation of black hole entropy at the correspondence point. And I emphasize again that this is not an exact accounting of the entropy. It's just telling us that some puzzles that that one encounters when thinking about rotating black holes can actually be solved, and they have to do with taking into account the dynamics. And one has to take into account timescales in order to be able to achieve adiabatic transitions, and so one has to think about decay rates. I mentioned that this process of transitioning from a black hole to a string and back can be realized either by evaporation or by a dilaton wave. And this applies to generic black holes in general dimensions. So I've now generalized this to rotating black holes. And this is only the starting point, really, because actually what we wanted to do originally was add the effect of self-gravitation for rotating black holes. And then we encountered that actually there are so many puzzles involved with thinking about high-dimensional rotating black holes that we first had to understand what should actually transition into what, and what is relevant in this discussion. But it would, of course, be extremely interesting to add the effect of self-gravitation, in particular to account for the matching of the sizes of the black holes and the strings when rotation is added. And this would go beyond this recent work of Chen, Malasena, and Witten, which expanded on the Horowitz-Polchinski result in various ways and by adding charge. And I believe there's also upcoming work by Santos and Zigdon on this question of the black hole string correspondence when rotation is added. So look out for that. And other questions are adding charges. So what happens for Carnuma black holes or the high-dimensional analogs. And then finally, it would also be very interesting, in particular in light of the recent discussions and new results, to understand what happens near extremality, where things seem to be a bit different. Okay, I'm done.
Questions?
So maybe I can ask you about this adiabatic thing again. So in the argument you gave, there was some delta S proportional to temperature times delta T.
Yes.
What is the mathematical underpinning of that? So in this Goldilocks thing.
What do you mean, the mathematical underpinning?
Like this, so why is delta S equal to temperature times delta T?
This?
Yeah.
So when you have a temperature, then you emit a quantum every thermal time, which is 1/T. And then the
But
total
why
change,
is the change of entropy of the system that emitted that equal to that temperature? Like, it's not necessarily the case, right? That I mean, so this is like counting how many quanta were emitted, right? And this S, as far as, so we are interpreting this S as some kind of microscopic count of states, right? That's what we want to match. So why is that change of entropy equal to the number of quanta that were emitted?
Well, okay, first, naively speaking, if you emit something, you lose entropy. And then is your question, why is it given by exactly this combination of T and delta T, or?
Well, I guess I'm saying there are two notions of entropy. One is like a microscopic counting of the degrees of freedom. And one is some thermodynamic kind of entropy, like which we use in thermodynamics. This seems like the thermodynamic one, right?
Yeah.
But the thing we actually want to match is the microcanon, or like the microscopic entropy, some log omega. I guess I'm confused between the relation between those two. You seem to be using some thermodynamic arguments like this to reason about quantities like log omega. That's my
okay, we're first trying to gain a rough picture of this correspondence and what the relevant scales are. We're not going into the details of the microscopic underpinnings. We cannot get the precise factor. We're just trying to understand as things go up, well, as things increase or decrease, how they scale with the relevant units and the relevant scales.
Well, that I understand. Like, I'm not worried about the overall factor being right or not, but
you want some more microscopic interpretation of this range of adiabaticity. Is that what you're asking?
Yeah, or like what this idea, because I think, like Emil was saying, there is a way of understanding this without talking about adiabatic changes. Like, just we can plot energy on the x-axis and just study the states in the theory as a function of the energy. And then one doesn't need to talk about this adiabatic thing at all. So maybe I should ask, like, is there a way of doing that for the rotating black hole as well, where you just think of the microcanonical parameters E and J, and we keep little g small and fixed, we never change it, and then we get a picture of the states as a function in the E comma J plane?
Perhaps there is, and that would be a refinement of this analysis.
Okay.
Would be good to think about. Yeah.
Okay. I would just, so I really enjoyed this correspondence. It looks very detailed. I was just wondering if there is one more thing you could possibly try to compare between the string and the black hole, which was very useful to us in the early days of understanding fuzzballs. The low energy absorption cross-section or emission cross-section is very different between a string and a black hole, because a string emits all spins with equal probability. It doesn't care which ones you're emitting, how they are polarized. But the emission from a black hole is very different between the directions which are in the compact directions and those which are in the non-compact directions. They are suppressed by factors of the frequency upon area. And that difference actually shows you that the transition from the string phase to the black hole is not a crossover like Emil was saying. it has to be a phase transition because new degrees of freedom have to interpolate. But it could be a much more intricate comparison of that issue with what you have now.
I think for that to match, you'd also need to take into account self-gravitation, no? So
say again, please.
Self-gravitation, which is what we haven't discussed here. So even just much simpler thing that doesn't match if you just look at free strings and black holes is the size of the object, right? And for that, you needed self-gravitation in order to match them. And so for your emission rates, I imagine since they don't match, you would also have to take into account self-gravitation. And I don't remember now whether this hasn't already been done for a study case at least. But it is definitely something interesting and that we could add also for the rotating case. And Emil has a comment on this.
Thanks. Emil, here's the...
Yeah, it sounds like what you want to compare is okay. It sounds like what you want is a comparison between the two-point function in the Euclidean black hole and the Horowitz-Polchinski solution. That would be the analog of, looking at the...
Do you know if this has been done in the study case?
I don't know.
I don't remember now.
But I mean, the two solutions exist, and presumably it wouldn't be too hard to compute.
That's what I'm asking.
So I have a couple of very quick questions, which are, related to the questions that has been asked, but also coming from my own ignorance. So first thing is that, so is it correct that when you talk about adiabatic transitions, you're talking about slowly varying the coupling, which you call G? If that is so, then is it possible to understand? Sometimes it happens that when you change a coupling constant abruptly very, very fast, certain universal laws appear. So I'm just wondering whether that limit, which is exactly opposite of your adiabatic limit, is analytically tractable. That's question one. The other question is, sorry.
So the correspondence point is at 1 over the entropy. If the entropy is large, then that is a small value.
No, I was thinking purely in terms of changing the coupling. Yeah. So if I somehow manage to change the coupling abruptly fast, like a quench, for example, does that give you additional analytic handle on the transition, on the nature of the transition, for example?
So that would, I think, mean that if you keep the entropy fixed, that the mass changes abruptly.
Yes.
Which is not something that we want. We would like it to be a smooth transition between the masses.
Okay. And the other related question was that, I saw some, you had certain formula for partition function, at least from the string side, right? So the string partition function, does it depend explicitly on the coupling constant? And if it does, is it possible to see whether the partition function develops singularity or zeros if you try to tune it to the transition point?
So here I'm talking about free strings.
Yes.
And this is just given in terms of the temperature and the level. And then the space-time dimension comes in. And if I add rotation, I also have that extra parameter there.
So it doesn't depend on G at all. I see.
Computing this for free strings.
Okay, I understand.
Okay, let's thank Andrea again.